All right. So the whole point is to estimate a system's response to an input. So the general problem we're trying to solve is that we have some arbitrary input x of t. We have a system, and we want to estimate the output, right? That's the name of the game. So far I've given you one option. And that one option was convert your input signal into a frequency domain, to multiply it by the system transfer function, and that will give you the Fourier transform of your output. Okay, so that's cool. That works. Now we have to look at the other avenue. The other avenue, so that's a frequency-based approach to finding your solution. Today we're going to examine the time-based approach to estimating your system output. So here's what we're going to do. What did we learn is the inverse Fourier transform of the transfer function. What goes up here? What goes in this block?
Whatever you're multiplying by.
We're not multiplying.
The impulse.
Impulse response, h of t. Okay, so remember, in order to go from the top row to the bottom row, you take the Fourier transform. So the Fourier transform of x of t is x of omega. The Fourier transform of the impulse response is the transfer function, right? Let's write that down. Fourier transform of impulse response is transfer function. Okay. So let's work this. So what we want to know is, so we know what h of t is. H of t is the impulse response. All right, so let's play a game. Let's say this is my input signal. Here's 0. Here's t. And let's say my input is an impulse. Trick question. What's the output? If my input is an impulse, what is my output going to be?
It's going to be h of t, your input, your impulse.
Yeah, it's just going to be the system response to an impulse, which we've already said, generically speaking, h of t. Okay. I have an idea. What if my input signal, instead of being delta of t, was shifted over, like to, let's say, can I shift it over by some time, by just some number tau? So let's say this is my input now. Delta of t shifted to the right by tau units. So what's my output going to be? If I shift my impulse by tau units, what's my output going to be? Yeah, h of t shifted to the right by tau units. It's common sense, right? If you delay your impulse by 1 second, you get your impulse response delayed by 1 second. Okay. What if I scale my impulse? What if I multiply it by like 2? What happens to my impulse response? Scale by the same amount, right? So, and that's kind of what I want you to hold on to. If I take an impulse and either shift it or scale it, then what I'm going to get is an impulse response that is shifted and scaled accordingly. All right? Oh, you roll your eyes. Did we really get out of bed for this nonsense? Yes. Okay. Now, here comes the magic-y part. Suppose your signal, x of t, is not an impulse. Suppose it is some arbitrary signal. You ready? I claim that if you squint your eyes and think about it hard enough, you could imagine that this x of t is really just a sequence of impulses, right? Like this is an impulse, and this is an impulse, and this is an impulse, and so on. Isn't that right? So, if I want to know my system's response to this arbitrary signal x of t, all I need to do is find the impulse response for each of those impulses and add them up. Isn't that right? I mean, this is an impulse, so I'll get an impulse response. This is an impulse. It's shifted and it's scaled a little bit, but okay, it'll produce an impulse response that's shifted and scaled a little bit, right? And I'm going to do that with all my impulses and add them all together because they all contribute to the output. So let's build that. Let's look at this particular impulse, okay? This arbitrary impulse. Let's say this impulse occurs at time tau. So first question, what is the amplitude, how big is that impulse? Is it area 1, area 3? How do I know the area of that impulse? Exactly. The area of that impulse is like the height of the function. And the height of that function is x, x not at generic time t, but specifically it's x at time tau. All right? So, what is the response to that impulse? The response to that impulse is going to be my impulse response h, shifted to the right by, okay, is that shifted to the right by tau units?
Yes.
Okay. And scaled by x of tau. So far, so good? That's the system response for that impulse. Now, how many impulses do I have? Okay, so I did one of them, right? But now I got to do the rest of them, right? I mean, I've got this tau, but I've got this tau and this tau, all these other taus. So I need to add together the responses from all those other taus. How do I do that?
Infinite series.
It's an infinite series, but really there's so many of them, they're like so close together. And there's a trick that we do when we want to add an infinite number of things that are infinitely close together. We integrate. So what I'm going to do is I'm going to take this expression, which is a scaled and shifted impulse, and I'm going to add it, well, basically I'm going to integrate it over all values of tau, right? Because I want to do this tau and this tau and this tau, and I want to do all the different values of tau. Like, if this were discrete sums, I would want to sum it over all values of tau, right? But there's so many taus, and they're infinitely close together, that instead of doing a discrete sum over all values of tau, I'm going to do the continuous version of that, which is essentially to integrate it over all tau. It's a little bit like that, but in time. And which taus do you want to do? You just want to do all taus, like basically minus infinity to infinity. Right? Just integrate it over all time. And that, my friends, is the much feared, much talked about, much maligned convolution integral. So all it is scaled and shifted impulses summed over all possible impulses in your input. That's it. Now, actually running that integral is a headache, like actually computing it, but mathematically that's what it is. So right away you've learned something interesting. In the frequency domain, you calculate the output by multiplying the Fourier transform of the input with the transfer function. That's in the frequency domain. But the equivalent operation in the time domain is not to multiply x and h, right? I know some of you were kind of thinking along those lines on Monday, but in fact, what you're doing, instead of multiplying x of t and h of t, you are convolving them. Right? That little star with a circle around it, that's the shorthand. That's what this is called. That's just the shorthand for convolution integral. You say x of t convolved with h of t. What do you think? Messed up. But it works. So, here's... What's that? Ask questions. There's going to be a lot of them.
Okay. I'm just, is H, do we have to figure out H of t in this case, or is it normally given to us? I'm just trying to...
Well, h of t will vary depending on the system.
On the circuit.
Yeah, on the circuit or the system or whatever, right? I mean, it doesn't even have to be a circuit. Any system, if I kick this bench and it shakes, that's a system, right? My kick is an impulse, right? It's a singular blow of energy to the system. And then, the bench might wiggle a little bit and then eventually stop wiggling, okay? That's a system. It's got an impulse response, right? Like if your car, if you're driving your car and you hit a pothole and your car, does like a couple bounces and then stops, that's an impulse response, right? You've kicked it with a single pulse of energy and then it responds. So impulse responses aren't just confined to circuits. But we are going to think about them in terms of circuits. But every circuit would have its own impulse response. Oh, we're going to do examples. Yes.
How would you go about finding h of t? Do you need to solve the differential equation for the special case?
The easiest thing to do, well, there's a couple ways you could do it. One way is you could actually get the transfer function and take its inverse Fourier transform.
Okay.
That's one way. Another way is to use the differential equation to get the step response and then differentiate it.
Okay.
Because the derivative of the step response will always be the impulse response.
Would that be the best way of going about it as a mechanical system versus an electrical system?
I don't really know. That's a good question. My experience has been I know for circuits, sometimes it's easier to do it one way and sometimes it's easier to do it the other way. And quite frankly, it's not something you're going to spend a lot of time actually doing. It's something that's critical that you understand conceptually, but from a circuit design standpoint, you're not going to spend a whole lot of time finding impulse responses of systems. But you need to understand how it works because it plays some other roles that wind up being crucial. But in terms of actual circuit design, I've never sat down and said, I need to design a low-pass filter. Let's start by looking at the impulse response. It just doesn't, that's just not how it works. You need to be mindful of it. Yes, you had a question?
Yeah, you were saying to get the step response and then the impulse response by taking the derivative.
Yes.
And most of the time we should use the Z resistance, what is it called?
Impedance.
Impedance.
Yes.
Okay.
Right. Well, if you're doing the impedance, that's the frequency approach. That's the transfer function.
We won't have, and then we do the inverse.
Inverse, and then you don't have to take the derivative, right? Because then you just backed into it, so you're good to go. Okay, so let's talk about how this works from two different ways. So all the examples I'm going to work today are a system that we already know how it's going to behave, right? So the system we already know how it behaves is the lowly RC filter, right? And we already know two things about this thing. We've already calculated, I think just last lecture, that the impulse response is 1 over RC e to the minus t over RC. Have we not already calculated that? Okay. We also know that if your input is a step, right, if that's your x of t, we know that your y of t, in response to that specific step, is 1 minus e to the minus t over RC, which is basically what you get when the capacitor charges up to its final value. Right? So we know all this. This you've known from your time in the womb, right? It's so intuitive that you were all born knowing this. This we just calculated on Monday, okay? But what we're going to do before the lecture is over is we're going to use the convolution integral. We're going to convolve x of t with h of t and verify that in fact we get what we all know is the right answer is the step response. Okay? All right. Before we do that, I do want to do a graphical analysis of this because I think it's helpful. So when our input is a step, all right, so if my input is a step, so my output, so let's say at time t equals 0, I've got an impulse. So that impulse is going to generate an impulse response, which I'm going to attempt to draw cleanly. It would probably just be easier if I turned on my laptop and showed you the picture from the book, which I think a lot of you have already seen. Okay, so there's the impulse response from one impulse, right? Now, I've got another impulse. That impulse is going to be shifted, but it's going to be the same size as the first one, right? Okay, so it's going to be shifted, but the same size. And then there's going to be another impulse, which is shifted, but the same size. And so on and so forth. Okay? So, if you wanted to know what the system response was at some value of y, like let's say this is time t1. If you wanted to know what the value of y was at time t1, what you would have to do is say, well, the first impulse gave me this much, and the second impulse gave me this much, and the third impulse gave me this much, and actually there's an infinite number of impulse responses that are going to pass through that time, right? So essentially what you would need to do to get y of t1 is to add together all those impulse responses at that time. And that's exactly what the convolution integral is doing. Right? It's saying if you want to know y at this time, then you've got to use the convolution integral. Right? You've got to integrate over all t, x of tau, h of t minus tau, d tau, and what that effectively does is it adds all those together and will tell you what the response is at that time. Sick, but it works. Okay, so let's actually try my example. We're going to take this input, which is a step, we're going to convolve it with this impulse response, and we're going to verify that in fact the result of the convolution is the step response, which we know this is going to be, we're expecting this to be our answer. All right, if we get that answer, then we'll know we've done the convolution correctly. If not, no, I lose my job. I'm just kidding. I'm tenured now. You can't fire me. I don't have to show up to work anymore. I just come because I'm a nice guy. But I could stop anytime. All right. So, that's not really true. Y of t. I mean, I can get fired from my job, but it would require lots of unseemly behavior and some hearings. Okay, so integral over all time of x of tau, h of t minus tau, d tau. So I'm just writing the integral, right? That's what we've already decided. So let's build the pieces for this. Okay, so x of tau, we know that our input x of t is it's 1 for t greater than 0 and 0 for t less than 0, right? That's my step input. Okay, that's good. And my h of t is the same thing. H of t is 1 over RC, e to the minus t over RC for t greater than 0, and it's 0 for t less than 0. Are we in agreement? Okay. So, if x of t is 1, what is x of tau? Just 1, right? So this is where people start to fall apart on convolution. mind your t's and your tau's. Okay? They ain't the same. Okay? If you can be mindful of them, you'll reduce the complexity of this task by half. So, but in this case, I need x of tau, and this one's easy because it's just 1. Okay, so x of tau is 1. So I'm actually going to go ahead and draw that. So I'm now drawing this versus this is my tau axis. Okay, because I was told to plot x of tau. So I'm doing like a units change. Instead of plotting it versus time, I'm plotting it versus tau. Okay, because that's what I want, x of tau. There's x of tau. This is tau equals 0. Are we okay so far?
So that's was your step shifted? No, right?
Nope, there's no shift in my step. Yes, sir.
Quick question. Your definitions up there are in terms of tau, the x of tau and h tau.
These?
Yes.
No, these are the input signals, which were
Okay.
originally stated with respect to time.
Okay.
Right?
Just make sure you're
Originally,
nice
when I defined my step response,
and they're in terms of time.
it's in terms of time.
That's what I thought. I just wanted to make sure that I'm
Right.
reading
No,
your
no, you're reading it
tau.
correctly.
But
Okay.
your tau,
Now it's going to get tricky.
your tau,
Right.
your tau starts at 0 when your step goes up, right?
Right.
Your tau starts.
Okay. So let's look at that. Right. So let's look at this now, because now I need h of t minus tau. So hold on.
See in front of you.
Okay, sorry, I'm back now. It is detail. Okay, so let's look at h of t. Now this is h of t, right? That's your stated input. But what I need is not h of t. What I need is h of t minus tau. Okay, so how am I going to deal with that?
Substitution.
Yeah, right? Everywhere I see a t, I replace it with t minus tau, right? I'm essentially, instead of h of t, I want h of t minus tau. And that's easy, because all I'm doing, everywhere I see a t, I'm replacing it with t minus tau. Okay, so I think what that's telling me is that h of t minus tau equals 1 over RC e to the minus t minus tau over RC. See what I've done? All I did, there was a t, I've replaced that t with t minus tau. Okay, now I'm going to plot that, all right, for some value of t. So what is that? So I know that h of t h of, actually, you know what? Let's skip the plot for a minute. I am going to come back to the plot, but I don't want to overly complicate this on the first pass. I'm just going to forget about the plot for a second. Well, let's just do the integral and make sure we get the right answer and build some confidence. Then we'll come back and kind of deal, I think, with a little bit more of the nitty-gritty of the h of tau, because it gets, there's some like subtleties to it. They become time-consuming. Why don't we just run the integral? Okay? So we've got h of t minus tau. I'm happy. So let's just plug and chug, right? It's a formula. We've got a formula. We've got x of tau. We've got h of t minus tau. No stopping us now, right? Let's just integrate it. So I'm going to integrate. So y of t is going to be the integral of x of tau, which is 1, times h of t minus tau, which is 1 over RC, e to the minus t minus tau over RC, d tau. What's that? 0 to infinity. Now let's talk about those limits of integration for a minute. We're going to come back and talk about those limits of integration in more detail because they vary. But in this case, I think we can just reason our way through it. Our input starts at 0 time. Our impulse response starts at 0 time. Therefore, there's no point, like when you're looking at those scaled and shifted impulses, there are no scaled and shifted impulses that occur before tau equals 0, right? There's no impulse, there's no system, there's no input, sorry, before 0. So therefore, there are no shifted impulses at negative times. So we only need to integrate over positive times. But we do need to integrate over all positive times. So we do have to go out to positive infinity. Okay, now we're in calculus zone. So the 1 over RC comes out, because that's a constant. And now I've got, let me just do a little scratch paper over here. If I distribute this exponent, look what happens. I've got e to the minus t plus tau over RC. Is that right? Could I also say that that's equal to e to the minus t over RC times e to the tau over RC? Can I say that? Yes. Ah, now what am I integrating with respect to? Tau. So if I'm integrating with respect to tau, guess what's happening to this guy? Constant. Does not vary with respect to tau. So we can take that whole term and bring it out of the integral. So e to the minus t over RC. And now we're left with the bit that we actually have to integrate, 0 to infinity, e to the tau over RC d tau. Hey, even I can do that. All right, so how do I integrate e to the tau over RC? Careful. Well, it's all this stuff.
It's RC, all that stuff, RC, e to the tau.
Right. It's 1 over whatever the multiplier of the tau is. Okay, and the multiplier of the tau is 1 over RC. So you're going to be left with all the stuff that was there before times RC, and then the integral is e to the tau over RC on the limits from 0 to infinity. I feel like there's a minus missing in here. Where have I lost a minus sign? E to the minus tau over RC. Something here doesn't smell right. Because e to the... It's going to be infinity. Did I botch this? Yeah, wow, it's right. How did I screw this up? Hold on. Does everybody see why I got confused? Okay. Yeah, I mean, if I sub in infinity for tau, that doesn't make sense. So at least my baloney sensor went off, and I figured out that doesn't look right. So hold on. So let's see. H of t is 1 minus, is definitely that. That's right. So if I now do h of t minus tau, what I'm supposed to do is 1 over RC e to the minus oh, I screw this up every year, don't I? That's not a good thing, is it? Okay. I screw this up every year, and I'm going to screw it up again for you guys, so perhaps it'll be like a rite of passage. Okay. Let's work our way. No, but this is instructive. And I'm sincere in saying that. Like, I don't claim to always have the answers, and neither should you. But you should claim to have enough common sense to scrap your way out of a corner when you get in there. Okay? So what I'm hoping to demonstrate is that you can actually figure this stuff out for yourself, and it ain't awful. All right? I think that's a useful lesson. So let's try that. Again, my goal is to get to h of t minus tau. And I think my statement that you can just substitute in t minus tau for t was incorrect. So let's actually work our way through it. Now, one thing that you can definitely do is just replace the t with a tau. That's definitely legitimate. Right? Because that's just a substitution. Now, if I want to, let's see. If I want to do h of minus tau, right, so h of minus tau ought to look like, if h of t and h of tau look like this, what's h of minus tau going to look like? Exactly, it's going to be flipped the opposite direction. So what's that expression going to be? That should just be 1 over RC e to the positive tau over RC for what values of tau? Right, for tau less than 0. I guess we are going to have to do the plot, is the short answer to my question. I tried to be slick. Okay, now I need h of t minus tau. And here's where it gets tricky. So what happens now? Did I screw that up? Hold on, I'm just... Yeah, I know what my problem is. I suck. Okay, I know what the problem is. The problem is it's definitely not in... No. The function is correct. The problem is that this is not infinity. Okay, sucky professor. All right, put that in your notes. All right. We should have just done the plot. That's all I'm trying to say. What? What? Yes.
Well, no, I was just going to ask, would it be from, I guess, 0 to 2?
Yes.
Okay, it's because of the shift.
Yes. Yes. But now we're going to talk about why, so that everybody's on the same page. Okay. So, okay. Turns out we weren't all that wrong, but a little bit of fix we needed to do. Okay. So now I need h of t minus tau. Now that my function is with respect to tau, adding a t is like a shift. Right? Like if I said h of 4 minus tau, that would be a shift, right? The question is, am I shifting left or shifting right? And it ain't obvious. Okay, here's how you can figure this out. Let's just stick in a number here. Let's just say t equaled, I don't know, 4. This is literally how I do this when I get confused, right? You can always work your way out of this corner. So let's see, what would h of 4 minus tau look like? And here's how I would work it. Okay, right. So if it's 1 over RC e to the minus tau over RC, this function starts at tau equals 0, right? It starts when your whatever the numerator of that exponent is 0. So same thing for here. If I've got 1 over RC e to the minus 4 minus tau over RC, what value of tau is going to make that numerator 0? 4. All right. So if I put a 4 here, then in essence what I've done is I've shifted it to the right by 4 units. Which is weird because usually when you do a positive t, it's a shift to the left. But because I've got a negative tau, it's actually a shift to the right. Okay. So I am actually going to do the drawing now. So I was correct in saying that this is e to the minus t minus tau. That's correct. So what we wrote originally is correct. But let's go ahead and do the plot. So here's x of tau, which starts at tau equals 0. Correct? Now, here is h of t minus tau. Are you with me? Is that h of t minus tau? Look at the drawings that we did. We started with h of t, then we said h of tau, well that was the same thing. Then we said h of minus tau, and the h of minus tau had the effect of flipping it, right? H of minus tau flipped it, and then we did h of t minus tau, which had the effect of taking our flipped signal and shifting it to the right by how many units? T units. That's where we screwed up.
So we're making this dependent on tau instead of t.
Yes.
Okay.
Because the integral is d tau. Yes, sir.
So,
I get that this is confusing. I've done this before. Yes.
yeah, so the last one is the, never mind.
Right? So this is what it looks like for h of t minus tau. So again, to summarize the steps. We started with h of t. We converted to h of tau. That was just a change of variable. Nothing changed. Then we did h of minus tau, which had the effect of taking our impulse response and flipping it. And then we said, let's shift it by t units. So now we're going to shift it to the right by t units. Yes, sir.
So it didn't work for infinity because we had no signal at infinity. It was just 0.
That's right. Yes, sir. Yeah.
Then left t since t is positive, or
No, because it's versus tau now. It's versus tau. So it's a right shift. It's a right shift because my independent variable is tau, and up here in the parentheses I've negated it. So because it's negative, everything's opposite. Okay, so look at the convolution integral. The convolution says to take x and h of t minus tau and multiply them. Doesn't it? I mean, isn't that the very definition of, well, I don't even have it up here anymore, right? The convolution says integrate x of tau, h of t minus tau over all values of tau. So if I multiply those two functions together, where is the non-zero integral? Do I need to integrate negative taus? Why not? If I integrate negative taus, well, I have x of tau, h of t minus tau. Well, x of tau is 0 for negative taus. So there's nothing to integrate. Okay, so I know I can start my integral at 0. Now, how far out do I need to go on the right? Do I need to integrate all the way to infinity? No, that was my mistake. How far out do I need to integrate? T. Why t? Because after t, this function is 0, so their product will be 0. Okay, so I only need to integrate from 0 to t. Sucky professor. Look at that. I apologize. You people deserve better. Okay. Luckily, you know, the integral didn't really change much. Right? I mean, we did the integral right. It was just a limit that was wrong. Okay, and we're back now. Okay, so good. Hey, did you notice the RC's cancel? That's nice. So let's see. We've got e to the minus t over RC. Okay, because that's that term. And now I'm going to sub in my limits of integration. So let's see what we have. If I do that, I'm going to sub in t and 0 in for tau. So it'll be e to the t over RC minus e to the 0 over RC. And e to the 0 is 1. Oh boy. Okay. Can somebody help me through the last step? What happens when I multiply those together? I get 1 because it's e to the minus t over RC times e to the positive t over RC. You add the exponents. You get 0 for the exponent. E to the 0 is 1 minus e to the minus t over RC. And it worked. Hooray. Is that what we expected? You bet. Yeah, how far down? Were you okay to hear? Here? Okay. So did you understand where this step came from?
yeah.
Okay. So, I had e to the tau over RC. I just substituted in t for tau and then 0 for tau. So this was e to the 0 over RC. And e to the 0 over RC is just the same as 1. And now I'm going to distribute, I'm going to take each of these terms and multiply it by e to the minus t over RC. So for the first term, I've got e to the minus t over RC times e to the positive t over RC. That's this times this. And if you have two things that are the same, you can just add their exponents. And you add their exponent, you get 0. And e to the 0, oh, that's so cool, right? It totally works. So now you have the power that I could give you any input. I could give you a cosine for an input. I won't, but I could.
Thank God.
It's actually kind of cool. I've done it. You fill like 4 pages of calculus, and you get the right answer. You're like, yeah, that's kind of neat. Okay, but I can give you any signal x of t, and you can find the answer. All right. So, for example, yes, sir.
Still only for low pass filter.
Well, that particular example was for a low-pass filter because we use the impulse response of a low-pass filter. Okay, so maybe we could ask an interesting question, which would be, hold on, let me think through this before I get in over my head. Am I going to get in over my head? I might. Let's do it anyway. Okay. Okay.
What about if we just do a high pass filter from scratch?
Yes, so let's do a high-pass filter from scratch. Okay, you want to try that? Just a simple high-pass filter. So if you want to do a high-pass, right? Well, the simplest high-pass you can get looks like that. What do you think the step response looks for a filter like that? Actually, you know what? Let's which way are we going to do this? So we need, okay, if we want to work with a high-pass filter, the first thing we need is the impulse response. Correct? I got 2 methods. Method number 1 is
Find transfer function that take the inverse Fourier.
right. So if I want to find h of t, option 1 is find h of omega and then take inverse Fourier transform. And method number 2 is take the differential equation, use the differential equation to get the step response, and then take the step response, take its derivative, you can get the impulse response. Both methods will give you the same answer, because there's only one right answer. Which of these is least off-putting?
First.
Let's find out. Yeah, that's my shorthand for inverse Fourier transform. Okay, so what is the transfer function for this thing? Let's see, this is R. What's the impedance of that capacitor? 1 over j omega c. And so this is just a voltage divider, right? So my transfer function is going to be R over R plus 1 over j omega RC.
Just the j omega.
Oh, just the j omega c. Correct, you are. All right, which equals, if I tidy that up, I'm pretty sure that gives me j omega RC over j omega RC plus 1. Sweet. Who knows how to take the inverse Fourier transform of that? This guy does.
I can just use a table.
No, look, we're going to learn something cool. What? What?
So pretty much when we take the Fourier transform of a square root, for example, we get a sinc function, right? We always
Yes.
do. So we had to like work backward, and what would give us that when we
Right.
when we take the Fourier transform? And it's not even.
No. You're going to get there. Watch this. Watch this. Watch this. You ready? what if I took this expression, I'm going to express it slightly differently. How about I rewrite it as j omega times RC times 1 over j omega RC plus 1. Is that not the same thing? Okay. What is the inverse Fourier transform of this term? Not the sinc function. We've seen this.
That's a low thing.
Yeah, isn't that the low pass filter?
Oh, yeah.
Isn't this guy here, when we did h of omega for the low pass filter, we had this impulse response, and we figured out that its Fourier transform was that, right? So will you believe me that the inverse Fourier transform of this term, by definition, because we've already done it once, has got to be 1 over RC e to the minus t over RC. Is that correct? Sure is. Good. Now, I'm going to take, now I've taken that function, so I've taken the inverse Fourier transform of that. Now, if I multiply the Fourier transform by RC, what do I do to the impulse response? Right, if I multiply the Fourier transform by RC, I'm going to take this guy and also multiply him by RC. Now, so far I've gotten the Fourier transform of that. Sorry, the inverse Fourier transform of this part is this impulse response. But I still have to take advantage, I still have to figure out what the effect is of multiplying by j omega.
That's differentiated. So will we integrate that? No.
No.
So do
What?
we just differentiate?
Yeah. We've learned this. What is the effect if you take a Fourier transform and multiply it by j omega, what is the equivalent operation in the time domain? Differentiation. So if I can take the derivative of that expression, what I'll be left with is the impulse response of the high-pass filter. Isn't that cool? This is why we learn this stuff. Because you can quick...
merge like 4 lectures in the...
I know! And I wasn't even planning it. That was the best part. Right. I mean, this is like 4 lectures mushed into one. Look at this. Low-pass filter. We know that inverse Fourier transform because we've already done it. If you scale the Fourier transform by RC, you scale the time equivalent by RC. And then if you take the Fourier transform and times by j omega, that's just the derivative. And we're done. Okay, now, we will finish this example on Friday because it is awesome. Okay? But I would like you to think about, this is not quite as trivial as you think it is, taking the derivative of e to the minus t over RC. You think it's easy? There's a little twist to it. But if we take advantage of that twist, we'll be good to go. I'll give you a hint.
Yeah.
Plot it. E to the minus t over RC looks like that, doesn't it?
Worry about an impulse?
Yes. You have to not just take the derivative of this part, which is easy, but you've also, when you take your derivative, got to realize that at t equals 0, there's an impulse, right? You gotta take that into account. Otherwise, it won't work out.
Even though that's not an infinite,
That's an impulse. At this
that's
point,
not a cusp though.
what's that?
It's not a cusp.
What do you mean?
Like, so it's not an infinite slope, right?
Sure it is. Right here? No, this is your e to the minus t over RC only applies for positive times.
Okay.
So for negative times, you get 0. Right? For positive times, it starts over here at y equals 1 and then decays away.
So if it was a straight line connecting it, then it wouldn't be an impulse.
Right.
Alright.
Right. But it's not a straight line connecting it. There's an impulse here. So, if you really want to be, well, you could try the differential equation approach. I'd actually be kind of curious if somebody tried it and got the same answer. But anyway, we'll start on Friday by taking this derivative, and then we'll actually do some convolution and see if it works out. Now you've made some homework for me. I'm not gonna get caught and make the same mistake twice. All right, thank you.